Hello again, folks, in 113. Today, as promised, I'm going to shoot a video discussing the solutions for test number 3. Assuming by the time you've seen this, you probably have looked at the announcement. Let's see where that is, a PDF file. Now, here's just to verify, today is Tuesday, May 4th. May the 4th be with you, and also with you. My sister texted me that this morning, so that was my immediate reaction. Anyhow, we're going to cover this today. All right, I sent you information about Thursday. I'm going to mail you again, of course, on Thursday. But let's just look at this. All right, realistically, you want to spend your time finishing up your MAT-113. All right, let's see. This is the test number 3. It's a paper copy. It's not in the software. I had a person ask me, hey, you said that you sent it, but it's not in my lab. This is something I typed. All right, there's evidence of that, I hope. And we'll go through this. All right. Okay, so if you're following along, do print that out. And keep this when you're prepping for your practice, perhaps. Okay, let me turn my projector on here. We'll get going. If you hear ambient noises, that there's an ongoing renovation. I think I've mentioned it before, but they're knocking next door. Banging, knocking. All right. Let's see. Fix my projector here, so it's favoring the side. Okay. And get rid of the thumbnail. And expand this. All right. Remember that this is comprised of section 5.4, 5.5, chapter 9, and chapter 11. So the last test concluded with the sections of chapter 5 that were important, and this one begins with chapter 5, so don't be alarmed. All right, it's 5 and 5. Okay. All right, now let's see. All right. Let's see. The first thing you have to do is to factor the radical expression. All right. Remember, ideally, there's a little foot cloud. Ideally, when you have a radical, you would like to factor it into 2 parts. They're both still underneath the radical sign, right? But the first one you want to be the highest perfect square possible, or if it's a cube root, the highest perfect cube possible. Why? Because at least one of those 2 things, this one, if you choose that strategically, will remove the radical. All right? To take the square root of something that is a perfect square will leave you with a whole number, basically. So, and you might wonder, well, what about this? If you do that, then you probably won't have to worry about this. I would always double check it anyway. All right. What you end up with often is either a prime number that would not factor into anything but 1 and then itself, or a composite number that it would be like square root of 6. That would be impractical to factor further. It's just nothing is going to escape the radicals, so you might as well just keep it. All right. Now, when you think of something like 20 here, the radicand, all right, consider all the pairs of factors. 1 and 20. That's when they multiply would make 20, 2 and 10, and 4 and 5, all right? If you're going to factor this, and essentially what this is called here is the product rule of radicals, you're going to choose from these pairs of factors. Which of these is the highest perfect square possible? Everything includes the perfect square 1 as a factor. All right, but if you put 1 and 20 here, you have not made any progress, really. 4 would be the best choice for the reason I mentioned. It's the highest perfect square possible. And that means that this other part, the balance here, is 5, right? This, at least, will escape the radical. What is just the square root of 4? 2. So the end result is 2 times the square root of 5. And you might go, woohoo, why? Who cares? You know, isn't that this? You know, this is the same decimal if you check it with your calculator as the square root of 20. But the argument is, this is expressing the same quantity using smaller numbers. Therefore, it is simplified, right? And it's better than the decimal equivalent because it preserves all of the infinity that would be an irrational number. Like square root of 5 is an irrational number. It's infinitely stretching, and it has no pattern to it, so it cannot be transformed into a fraction. Right? The best that you could do is maybe round the decimal, but then you don't have the exact answer. This is exact and simplified. That is why it is the best answer. Right. Now when you're down here, it says subtract the radical expressions. The requirement in this case is that you, when you're adding or subtracting radicals, they have to have the same index, which is the type of radical, and they have to have the same radicand, which is the guts, basically, of it, the insides. All right, now you have 5 square root of 3, which is probably simplified, and then you have square root of 12, which is probably not simplified. So we're going to go about the process as we had before, the ideal situation of factoring this into maybe one chunk that could be ejected here. And you would end up with this, square root of 4 times square root of 3. All right, and then you have the same situation. The square root of 4 by itself is just 2, so this is 2 square root of 3. And then when you finally get it down to that point that you can add or subtract, you really just combine the outside, the coefficients technically. Well, I don't know if they're technically referred to a coefficient because that would imply that there is a variable here and there technically isn't. But it's behaving in a similar way. If you had a problem like, for example, 5x minus 2x, you probably at this point in your life wouldn't bat an eyelash. You go, it's just 3x. All right? Now, if that's the case, and now you're instead subtracting radicals, pretend that that's like a variable, all right? And this is what you would end up, 3 times the square root of 3, all right? You don't subtract the radicands, all right? The guts, you don't do 3 minus 3 and get 0, all right? You preserve that, all right? So this should be the outcome, 3 square root 3, okay? All right. Now here's an interesting one, rationalizing the denominator. Rationalizing the denominator is kind of a holdover from the time before calculators, in which you had to do everything by hand. And so if you were going to do everything by hand, you would be strategic and creating an equivalent ratio, all right, that doesn't have a radical in the denominator. All right? You can kind of think of it this way. There's no such thing as etiquette of math, but just for the sake of humor perhaps, think of good etiquette, all right, of math. All right? No radicals in the denominator. Okay? So what we're going to do instead is multiply by a convenient ratio equivalent to 1. I assume we agree, all right, that multiplying anything, even something ugly or complicated, by 1 is not changing its identity. It will change its appearance only. Now what you want to do when you have a radical in a denominator, at least if it's a square root, is basically replicate that, borrow that feature, right? You could be, when you get better at it, a little bit more strategic, right? But the convenient ratio of 1, and by ratio I mean something that has an obvious top and a bottom, that overall is equivalent to 1. If you choose to borrow the square root of 3 here, and use that as the bottom of your ratio, your convenient ratio, then as long as you put it in both places, the numerator and the denominator, that is equal to 1 unto itself, by itself, right? So even though it doesn't look like it, if you then distribute, more or less, the top and the top and the bottom and the bottom, you multiply, it may change the appearance of it, but it's not changing the overall value, all right? The benefit of doing this is that 1 times square root of 3 is square root of 3, all right? And square root of 3 on the bottom times square root of 3 on the bottom is square root of 3 squared, all right? These are opposite operations and essentially cancel one another. So this is the effect, which means that you have square root of 3 over 3, right? This is a rationalized denominator, right? This value, whatever the decimal equivalent is, square root of 3 over 3, is equal exactly to what it was. But the benefit of it is that you do not have a radical in the denominator. Why would someone not like that? Well, I'm just being funny when I say it's the good etiquette of math, waka waka, but the truth of the matter is it is less complex, right, dealing with a whole number as a denominator than, say, an irrational number, which the square root of 3 would be 1.7 something into infinity, right? So, if you were going to combine this with something else, right, you'd have less of a time of it, difficulty with a whole number as a denominator here. So, this is preferred, right? It equals that, but it is better in this condition, right? It's an equivalence. It's just rationalized. Okay. Now, down here we switch to section 5.5. Identify the property as either commutative, associative, or distributive. If you are familiar, if you have any experience with algebra, you've probably done a problem that is just like this, that they ask you to just expand this, which is to multiply the outside component by each of the inside components here. Right, and this is the result on the opposite side. All right, if this is 2x plus 3 as a result of multiplying the outside of the parentheses times each content of the inside of the parentheses, then what you have here is the distributive property. Right, you can apply the distributive property in arithmetic, and I've noticed that in recent history, in the United States at least, they've been sort of stressing that a lot. Right, when you see people get frustrated at sort of new math, for lack of a better phrase, there's no such thing as new math, it's just math. That's a lot of times what it is. It's basically taking something and making it a sum or a difference for the argument of the mental exercise, really, is what is the practical thing, all right, rather than do something in a more straightforward manner, all right? It's an alternative way of looking at something. This is looking at a problem this way, and this is looking at a problem or an expression this way, all right? It's really more practical, I would say, in algebra, right? But you can use it in arithmetic, all right? And you're inclined, if you're teaching elementary education in the United States, you're probably going to see something similar to this, all right? An expansion of some quantity as a sum, all right? It's a good mental exercise either way. Okay. All right, chapter 9. I felt compelled to explain this because it's a little alien. You know, this doesn't come up too often in American high schools, at least not in my own experience, either teaching or as a student. But it is interesting. Again, we could appreciate anything for the mental exercise. So, that's done. Don't use that. This one. Okay. This is about mathematical systems. A mathematical system is essentially a set, which is a list of numbers or something, and a binary operation, which is typically adding or subtracting. All right. A group is a more specific example of a system, and it must meet 4 criteria. All 4. Right? If it misses even one of them, it's not a group. Even more specifically, an abelian group would also have to meet a 5th criteria, the commutative property. Okay? So to do this problem that is underneath, I built a table here to help you get through it. All right? And it's just this one question after you get through here. We don't have a table, an array to pull tricks for the commutative property, so I went ahead and just put a check mark here as being, yeah, this is commutative. And it is also associative. That is true for the natural numbers. Check the group criteria for the set of natural numbers under multiplication, right? Is this mathematical system a group? We're going to decide that based upon really these three particular rules here, requirements. Because we're going to take, we already know, and this is for sure true, that natural numbers are associative and they are commutative, all right? Let me start by, just sort of expanding here this set. The natural numbers are the counting numbers that you could count on your hand, right? So it starts with 1, right? You can't obviously write all of them, but you could, put in a few and then put some ellipses to indicate that it progresses as such. Right, 1, 2, 3, 4, 5, 6, 7 into infinity. The whole numbers, but not including 0, right? Is the set closed under the operation of multiplication in this case? What does it mean to be closed under an operation? It means that if you perform the operation, in this case multiplication, does multiplying the elements only produce more of the same elements? In other words, if you multiply any two of these, any combination of two, do you end up with more natural numbers? And the answer to that is yes, right? This only produces more natural numbers. When multiplying. The same would be true if you were adding. Right? How about the identity element? Remember, the identity element is something that preserves the identity, right? Does the set include, there's an identity element, I should just mention this too, right? Here's a little quick diagram. There's an identity element typically for adding, and there's an identity element for multiplication, right? In the case of adding, it's 0, and in the case of multiplication, it's 1. Why is it 0 in addition and 1 for multiplication? Because anything times 0, anything plus 0 is equal to that thing. It preserves the identity of that thing. In the case of multiplication, anything times 1 is that thing. The number 1 preserves the identity here. So we're dealing with multiplication, all right? Is the number 1 included in the set of natural numbers here? And the answer to that is yes. All right, so far so good. All right, now the next thing is the inverses. All right, here's again a little diagram to remind you. When it comes to the inverse elements, all right, in the case of addition, that usually means the negatives. All right, in the case of multiplication, right, that means a fraction. That is it's a reciprocal. A numerator and a denominator flipped. Right? So for example, if you had the number 1, its inverse would be negative 1, right? What they produce in tandem with one another is the identity element for the operation. So what's 1 minus 1? 0, right? Which we've established is the identity element, right? In the case of multiplication, if you had, say, something like 2, right, the inverse would be its reciprocal, right? So I hope that's a little bit more obvious. This is an L. The reciprocal would be, since we're multiplying, 1 over 2. Right? And the result of that would be, again, when you perform the operation, it would produce the identity element. Right? What's 2 times a half? Right? It would be equal to 1, which we have, again, established as the identity element of multiplication. Right? Now, since we're dealing with multiplication and we're talking about reciprocals, we're really talking about fractions. Essentially, does this list contain any fractions whatsoever? It doesn't. Right? So the inverses for every element are non-existent in this set, right? And therefore we would say no, all right, the inverses are not included, all right, and therefore we don't pass the 4 criteria, all right, to qualify as a group at least, all right. So this is not a group, all right, because the inverses are not included. Like batteries not included. Okay. We would need to have fractions, and they're not going to happen here. Not for the natural numbers as a set, anyway. Okay. Next one. Here you have clock 12 arithmetic, which is an example of a finite system, natural numbers being an infinite system. And this is section 9.2. All right, now in this case, it would be practical to pull some tricks because we have a table here. I need some space, so I'm going to erase this. And we'll see, there's another little diagram here to keep track. I may have to shrink this. I just don't want to make it illegible. All right, here's the sort of criteria listed, all right, to use as a checkoff here. Let's see. Is the set closed? This is the first criteria for something being a system, a group. All right, and in this case, we're checking to see if it's an abelian group. We're going the whole 9 yards in this case. I'm jumping the gun a little bit. List in roster form the clock 12 arithmetic features, right? We're literally talking about elements, I should say. A clock literally has, right, 12 numbers, right? And it starts at 1. So just list them for your own sanity. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are the elements, and it's finite. And we said it starts at 1 and it ends at 12. No ellipses. It's not infinite. It's finite. Rather than play around with this, since it's finite, we could establish this table that is above here and dissect it to give us some information. Is the set closed under the operation? Now, let's go back and look at the top of this. Fortunately, I have to scroll back and forth. It's clock 12 arithmetic under addition, which is, you notice there's the operation up in the corner here. Do you, when you look at this, see anything other than these element numbers here? All right, is there a 13 in here? Is there a -5? Is there a fraction? Is there some weirdo decimal? Or is it exclusively 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in this table? All right. That's so you could tell whether it's closed without, attempting to, check the operation for each combination. Right? The answer to this is yes, it is closed. Right? Anything in the table that isn't an element? No. Right? Nothing. Right? Nothing weird. Right? In the table. So therefore, it is yes. Closed, right? Meets the first criterion, right? Number 2, identity elements included, right? The identity elements would be the intersection, right? In other words, you could identify the identity elements like 0 or 1, as in the infinite system, all right? By checking to see if the row heading and the column heading appear in the table, right? Do these appear in the table? All right, and the trick to this is that it has to be entirely, all right, and in order, as they are written in the row and the column headings. Here's what I mean. Let me free up a little bit. The row headings, I don't like the way that this was coded. The row headings are here. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the row headings. Okay. These up here are the column headings, naturally. what we're trying to do, this is a shortcut, is see if this row, exactly as it is, in order, 1, 2, 3, all the way to 12, appears in this table somewhere. Right? And then simultaneously, does the column heading, starting at 1 and running all the way to 12, does that also simultaneously appear in the table, which I wish, again, was a slightly different color than this different shade of, orange or whatever it is. Well, here, I'll do it in red here to highlight. All right, the column headings all the way down here in the table. All right, exactly as you see them here, they're here in the table simultaneously. The row headings are all the way over here. That's not always the case. Sometimes they're a little bit further in the middle. All right, exactly as you see them. All right, here. All right. Look where they intersect. They intersect right there, which is the number 12. All right. Therefore, that's the identity element. All right. Remember, when you have an element, and then the operation, whatever it is, combined with the inverse, right, you should get the identity element. Right? This is a way to verify that that is correct. Right? If you took an element and then you combined it with an inverse, which we haven't established what the inverses are yet. Right? Let's just take 1, for example, and then this is the operation plus. And we're assuming that this is the identity element 12, we can infer what the inverse would have to be. All right? 1 plus something that equals 12. All right? And then we would do with the next one, 2 plus something equals 12. And then the next one, 3 plus something equals 12, and so forth. Right? Let's go back to this just to check off here. All right? It is established. Yes, the system is closed. All right, there's nothing weird in the table, no extraneous sort of elements. The identity element is the point of intersection of the row heading and the column heading in the table, and that is the number 12 we have discovered. And now we're going to check this for inverses. Inverses for every element. All right, are there inverses for every element? All right. You could kind of see a diagonal line, all right? I don't really want to make that an established rule, but I'll show you what I mean by that in a minute. What's more important is really what I wrote here. The identity element is equal to the element plus the inverses. Now, go back to the table for a moment. All right. Look for the diagonal line that equals the identity element, all right? I'm going to just erase some of this because it's getting a little messy. And we're going to keep this model sort of in mind here, all right? If you start with 1 as an element, and you combined it with this column heading and this row heading, you see the number 12 here, all right? And if you do the number 2, all right, and you combine it with this 10, you see this same 12 here. And if you see this 3 here and this 9, you get 12 here. And there's kind of a pattern to this, which again, I don't know if this is official or not, but it's sort of an upward pointing diagonal line from this corner. There's another rule which I don't want to confuse you with. So I'm purposely not drawing a diagonal line, but look at this. All right. If this meets the third criterion, all right, then for every element and combined under the operation with its inverse, you should get the identity element. 1 and 11 apparently are inverses of each other because they produce 12. 2 and 10 are apparently inverses of each other because when combined via adding, they make 12. 3 and 9, 12. 4 and 8, 12. 5 and 7, 12. 6 in itself is 12. So it seems, having gone all the way from here to here, that indeed, and this should be, again, there should be a freaking line here. Whoever drew this needs to be slapped. All right. for not making this a little bit better. All right, it wasn't me, I swear, I slapped myself. All right, you see that there is indeed an inverse for each element, all right, by looking at this table. So we have met the third criterion, right? Yes, 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 right? Now, as is often the case with these problems, they will tell you straight out, you know, okay, yes, it is associative, right? I'm not aware of any shortcut using a table, right? What you would have to do in theory is test, you know, at least a few of combinations of the elements, all right, to see if they emulate the associative property. You know, I'm not going to do that, but here's the associative property, right? You can either add these two things first, or you could add these two things first, but they should produce the same result on this side and on this side, whatever the order, right? We're going to take for granted that it is in fact associative. The commutative property, right, of course would be this, two elements at a time. So A plus B is equal to B plus A, right? Right, you should get the same result, right, having things in this arrangement or this arrangement. Rather than do that for every combination, the shortcut when given a table is to look for symmetry about what is referred to as the main diagonal. This is why I was trying to avoid not talking about a diagonal line. All right, use this idea and really ultimately, all right, for that third criterion. All right, for this commutative criterion, all right, we're going to look for the main diagonal. We're going to look for specifically symmetry about the main diagonal. It's kind of as if there was a mirror that ran diagonally. Here's what I mean. So if you go back to the table here, the main diagonal officially stretches from the top left corner to the bottom right. All right. Any other diagonal is swell, but this is the main diagonal. So I'm going to try to not hurt myself here, as I often do with this ruler. Right. Draw a diagonal line here. And we'll see if there is in fact symmetry here. It's very faint, right? What you should see, if there is in fact symmetry about the main diagonal, essentially is that you'll see the same features on opposite sides of the line. Diagonal. So look here, right? It's 1 and 1, 2s, 3s, 4s, 5s, 6s, right? 3 6s this way, 3 6s here, all right, and so forth. So as you go through this, you see that there is nothing that breaks the symmetry, right? It's like this was a mirror and this is the reflection, you know, sort of, all right? So yes, it does indeed have symmetry about the main diagonal as you look down this line here, right? I may have to, you know, draw a little bit better, but forgive me. Anyhow, the bottom line is that it is in fact commutative, pulling the table tricks, right? So it meets all 5 criteria, therefore it would be classified as a commutative group, or otherwise known as an abelian group. This means commutative. Right, so yes, right, it is a commutative, quote unquote, abelian group as well, not just a group. Okay. Yeah, moving on. Section 9.3 is about modular arithmetic. Modular systems are finite, like the last, but they start always at 0. Right? They're cyclical, just as a finite system would be. Right? these are finite also, but always start at 0. Okay, there's some notations that we have to adapt to. Basically, a modulo M, or sometimes referred to as mod M system, and M is the modulus number, the number of elements in the set, consists of a set and then so many elements, and a binary operation. So it really is the same thing again. It's just that the slightly restricted criteria is that it must start at 0. All right. Because these are finite systems, i.e. have limited elements, they are cyclical in nature, and therefore would require that we express any larger quantities, something larger than the modulus maximum. Really, technically, isn't even the maximum, it's just shy of that. We express larger quantities in terms of the established elements only. This is known as congruence, and we use this symbol which looks like a glorified equal sign. All right, translating essentially what equals what in the specified system. Okay, so here's 2 examples to illustrate this. Problems. All right. In a mod 8 system, that's tenacious. In a mod 8 system, the set would consist of, again, starting at 0, 8 elements, but because you start at 0, it ends at 7. 7 is technically the maximum. All right. And if we divide any number by the modulus, in this case the modulus 8, the remainder would tell us what that number is congruent to. So if we had something like this, 60, which is not an element here, as you can see, we can translate it essentially into what it would be equivalent to in mod 8. So not too complicated. You're going to take 60 and you're going to divide by 8, right? And then look at the remainder. How many 8s can you squeeze into 60? 7 roughly, which is 56. And then the difference of them is 4. So remainder 4, right? Therefore, 60 is congruent to 4 in a mod 8 system. Right. Not too complicated, right? All right. A slightly more interesting problem that is based upon this idea is what follows here. Assuming days of the week are mod 7, right? And they would be, right? Because it's cyclical, we have a 7-day week established. It would therefore be, I wish it wasn't cut off here, but 0, 1, 2, 3, 4, 5, and stop at 6. All right, with 0 representing Sunday, 1 representing Monday, and so forth. All right, if today is Friday, all right, what day will it be 31 days in the future? All right, use your knowledge of the congruency to answer the question. Just be careful where you start from. So we're going to see what 31 would be equivalent to. All right, that's as if we started at 0 essentially. All right, we're going to have to adapt later, but we're going to see what 31 days would be equivalent to. You know, starting from here. All right. So we're going to divide by 7 and see what we get. 7 goes into 31 roughly how many times? 4 times, right? Which is 28, and the difference is how much? 3. That means that essentially 31 would be congruent to 3, right? But, right, if we want to answer the question, what day will it be starting from Friday instead, rather than starting from Sunday now, right? What we would need to do is basically have this set handy, 0, 1, 2, 3, 4, 5, 6, right? And from here, instead of 0 now, count 3 forward, right? So it's a little tricky because we have, it's cyclical in nature, so humor me. Start here, that's 1 jump, that's 2 jumps to 0, and that's 3 jumps on the 1, right? If Sunday is 0, what would 1 be, right? It's Monday. Okay. That's kind of neat, right? Let's do number 9. Let's see, moving on. Number 9. Okay, we're up to probability now. Calculate the theoretical probability of rolling an even on a 6-sided die. All right, remember there's theoretical probability, and as you see in the subsequent question, there's empirical probability. They're both probabilities, but one is based upon experiments, and the other is just based upon sort of a thought experiment, so an idea. It's abstract, whereas this is a little bit more concrete. Right? It's based upon actual events, empirical probability. Anyhow, the formula for theoretical probability is this. Probability of some event is equal to the number of outcomes favorable to the event, all right, over the number of outcomes in the set. Right? So if we're talking about an even, right, we could adapt this basic formula here. All right. Let me establish the set. Of the 6-sided die, what's the set? It's 1, 2, 3, 4, 5, 6. Right? Okay. So, if this is specifically an even, that's the event, the number of outcomes favorable to the event of it being even, right, would be what? How many essentially evens are there? 1, 2, 3, right? How many total outcomes are there in the sample of the set? There's 6, right? So if you reduce this, it's 1/2, and that's exactly equal to 50% chance to get an even, right? Which is logical, right? Now, here's something I stole from your MyLabs. I thought this was it. I didn't like the way it was worded, quite frankly. I thought it was a little misleading, so I tried to change that. All right, but this is to answer this question. Of the last 60 people to exit a theater, all right, 11 were blonde-haired, 20 were black-haired, 26 were brown-haired, and 3 were red-haired. So you have 11 blonde, 20 black, let's see, 26 brown, and 3 red. My sister, my oldest sister, the one that I mentioned, she has red hair. Anyhow, I can see that she's one of the freaks. Okay, she'd get mad at me for that. Okay. This is an empirical probability. The formula for empirical probability is the number of events, the probability of some event is equal to the frequency that actually observed over the number of trials. Right? Right. So frequency, right? Right. Total, or you might say trials if it's an experiment. Okay. So, calculate the empirical probability of someone with black hair based upon these statistics. All right? Someone with black hair, the frequency of them is 20 people. Right? The total number of people, and each person represents a trial, weirdly, right? But that's true. They're a person exiting the theater. All right? You would have to add these up. So that would be 11 plus 20 plus 26 plus 3. Let's see. That's 31. 31 plus 3 is 34. 34 plus 26 is 60. So what you end up with here is 20 over 60. Pull some tricks to simplify. If you have a pair of zeros, that's as if you divided each by 10. And then these are even, so divide each of these by 2. You end up with 1/3, or 1 out of 3, which is the same as 33 and a third percent chance. Right? Or 33 and a third percent of the time. Right? You want to phrase it that way because it's empirical. Okay? Alright. Here's another that I stole, because I like this one. I did draw this diagram myself, though, you know. I thought this was interesting. I do the homework assignments that I give you. Make sure everything goes according to plan, or at least as best I can. This was describing a beanbag toss game. This is a board. Alright. Using the diagram for the beanbag toss game, just randomly tossing a bag. Alright, calculate the probability of landing on a red portion of the board. Now, this is totally abstract, so you know, we're not doing this in real life. This is a theoretical probability. We're going to use that formula. Alright, that incarnation of the formula. Number of outcomes favorable to the event over the number and total in the sample, in this sample space. Is true if we're talking about a different problem, but in this set. Now, there's going to be a numerator and a denominator, so essentially a fraction, right? This is an area that we have no dimensions given to us, but we can infer a lot, right? Let's look at the largest sort of dissection here, the largest increment, right? The largest increment is one of these largest rectangles here, right? And we'll assume, as my lab assumed you would assume, that this is cut evenly, right? Everything is the same dimension here and here in spite of the color, all right? So, how many of these larger rectangles in theory would there be, all right? There would be one whole rectangle, that's the two triangles together, one whole rectangle, that thing, one whole rectangle, these two squares together, that's 3, and then these in unison would be another 1 and a 1 and another 1. So there would be 6 of these larger rectangles, all right? That's how we're going to establish the fractions, basically. Now, the actual question is calculate the probability of landing on a red portion of the board. And as you can see, there's different increments of that. So let's start with the obvious one. All right, it's going to be a sum, these fractions, perhaps 3 or more. All right, red areas. Again, we don't have inches, we don't have centimeters, we don't have any unit. We're just going to figure out as a ratio of the whole. All right. There's one of these red ones here that is a regular sized rectangle. All right, so this is 1/6 of the whole kit and caboodle. Right? This particular red rectangle is 1/6 because it's the dimension of 1 out of these 6 large rectangles. Okay? When you get to this one, for the moment, you could, if you want to, in your mind, assume that this dimension is equal to the dimensions of this square's dimensions of this square, and then chop up the whole thing even further. But what I think is a little bit, in other words, cut everything up into that shape and count them. You can do that. I think it's faster to look at it this way. This would be another 1/6, right? So, but we'd have to modify something. It would be 1/6 out of the whole area, but it's half of it. So it's 1/6 times a half. All right, to figure out just what this square would be proportionately. All right, then when you get to these up here, something similar. All right, I'm putting in these parentheses because it's something that you have to, a little calculation you have to do first, unless you're going to sit there and chop it up and count. All right, which is nothing wrong with that. I think this is a little bit more efficient. All right, this is again another 1/6 of the whole thing. All right, so it's 1/6, but it's not quite, it's not 3 rectangles here. All right, it's just 2 out of how many of this cut? It's 2 out of these 3, so it would be the same as 1/6 times 2/3. All right. Do what is in parentheses first. You're going to get a bunch of fractions with different denominators. You could use a calculator, but you can always practice writing equivalents. Right? What you would get in this instance is top times top, bottom times bottom is 1/12. And in this case, all right, you can simplify first. 2 divided by itself is 1. 6 divided by 2 is 3. Top times top, leftover times bottom is 1/9. So what you would end up having to do is add 1/6 to 1/12 to 1/9 to get exclusively thread areas, right? It's a little less satisfying than normal because we're so used to having a unit when we talk about an area, but you don't actually need it. You just have to think of this as being one whole, and then there's a chunk of that, a fraction of that one whole, hence the fractions, all right? You have to write these in equivalent fractions, right? The common denominator, ideally the lowest common denominator of 6, the same as the least common multiple of 12, 6 and 9, would be what? 36. So if you upgrade this to something over 36, and you upgrade this to something over 36, and you upgrade this to something over 36, they're going to proportionately change, right? 6 times 6 is 36. What's 1 times 6? 6/36 is the equivalent of 1/6. So we're going to save that equivalent. 12 times 3 is 36, and 1 times 3 is 3. 3/36 is the equivalent of 1/12. And then 9 times 4 is 36, so 1 times 4 is 4/36. All right, add that. Just add the tops. 6 plus 3 is 9. 9 plus 4 is 13. What you get is 13/36. All right, is the area, all right, of the board, all right, which is equivalent to the probability, all right, 13 over 36. If you want, you can divide this. This is an area out of one whole board. Right. So the one whole would be out of 36 out of 36, so 36/36. All right, that's one whole, 1, and this is a fraction of that. That's just the red portions. You could exchange this for a probability. It's the same difference, same thing, all right? And the probability can be expressed as a percentage if you like, all right? Which means that 13 divided by 36, you get a decimal. Just remember to multiply by 100. The effect is that this is about 36% of the total area. Okay? Most of the, I'm not sure because I didn't check the greens, but, or the yellows, but the red is more than 1/3 of the entire board here. 1/3 would be 33, you get a 3%. Okay? Okay. Number 12. All right, now we're talking about odds in favor and odds against. Remember, odds and probability, they're similar. One could derive the other via formulas that we have, right? But odds is either this ratio, A over B, right? And this is not the total, the bottom here. or you could write it as B over A. Right? Now, what is the difference between odds and probability? When you're discussing things from the perspective of odds, what you have is favorable over unfavorable. Or you can have that ratio switched. So you have unfavorable on top and favorable on the bottom, right? In this orientation of favorable on top, this is odds in favor, right? When you have it in this orientation, this is odds against. So we're reducing a fraction, but they're not probabilities, so do not convert them to percentages because it really wouldn't make sense. You could exceed 100% and that's not allowed. All right, this is for the purposes of gambling, essentially. Calculate the odds in favor. So we want things oriented this way. All right, we're drawing a queen at random from a standard deck of 52. All right. So if we're going with this basic formula here, favorable to a queen, how many queens are there in the deck of a standard 52 poker deck? Right? 4, right? How many things are essentially not queens, since that is unfavorable? Right? It would be 52 minus those particular 4 things, right? Which would be 48, right? Notice it's not, as in the case of probability, the total number of cards. Alright, it's 48. It's not the same thing. Odds is not probability, they're just remarkably similar looking. It's totally superficial. If you simplified this, divide by 4 each of these, you would end up with what? 1 to 12, right? Leave it in either the fraction style or you could use a colon like this. Alright, but don't make them a percentage. I'm talking about odds. One to 12. Okay, now the next question is the same thing, just upside down. Calculate the odds against, all right, drawing a queen at random from the standard deck of 52. Well, if we've established that this is the fraction in this orientation, what's the reciprocal of this? It would just be 12 over 1 instead, right? We could write 12 to 1. Like that or like this, but not as a percentage. No percents for odds. Okay. Let's see. Expected value. I like blue, but it doesn't go away. Calculate the expected value, a sort of average, if you will, not officially, but of good and bad probabilities. Remember, good and bad probabilities are fractions, essentially. Then you're going to add or subtract them depending upon the sign. All right. The formula for expected value is this, right? E for expected value is the probability, a first probability, times an amount associated with that probability. Plus a second probability and a second amount associated with that probability. And you could do this into infinities so that you get to the nth probability and its associated amount. All right. I like this question because I think it's relatable. All right. It says, on a multiple choice test, there are 4 possible answers, which means, you know, A, B, C, D. All right, to choose from for each question. The instructions indicate that it's 2 points for each correct. Right? A half a point for each incorrect. And no points, 0, will be added or subtracted for anything left blank, so no answer. Right? We can adapt this model to describe these conditions. Right? If it's four possible choices, and again, you can kind of envision this as A, B, C, D, multiple choice test, right? All right. How many, if we're gonna, this is the favorable probability. How many are correct, right, out of the total? Right? Essentially. Well, there's only one correct answer, right? So this first probability is 1 out of, how many choices are there? I should use S, but I mean total, you know. There's 4. So it's 1 out of 4 is that first probability for correctness, right? What's the amount of points awarded in relation to that? 2. So this would be 1/4 times 2 points. All right. Now let's establish the probability of incorrect out of the number in the set. All right. How many are incorrect out of 4 choices? There would be 3 out of 4. All right. How many points are you awarded in that case? Well, it's the way that it's phrased is 1/2 point will be lost, which means technically 1/2 point will be gained, right? But since we're discussing it from the perspective of lost here, all right, let's make this -1/2, right? Because of this phrase, lost, all right? You'd have to be a little careful if this fraction was somehow decided differently. It is 1/2, so you're going to use 1/2 no matter what, half correct or half incorrect. But when you get negative connotations of words, use negative, all right? That's why, again, I say this is something like an average because you're going to be adding and subtracting stuff, right? When you get into next semester, if you take MAT-113, there's something called standard deviation, and it is very much like that. You know, it's very much a sort of average of distances from the mean, all right? Anyhow, this next thing is really superfluous because of the nature of it. What if you're asking what is the probability of neither correct nor incorrect? Is that even possible? All right, it's not possible, right? The probability of there's only 2 conditions. It's totally binary. It's either incorrect or it's correct. There is no third choice, basically. All right, that's just not participating. So you could eliminate this. The result would have been anyhow no points, which would be whatever the probability was. You would be multiplying by 0. All right, so it would be. It's superfluous. You don't need that extra term. All right. Now, if you straighten this out, 2 times 1/4 is essentially 1/4, 1/4 times 2/1, right? Simplified, it's 1/2, right? So you have the expected value, the first term is positive 1/2 points, all right? And if you're dealing with the second one, the second term here, we're considering the incorrect, it is 3/4 or 3/4 times -1/2, right? Can't simplify up front, you end up having to do brute force, top times top, bottom times bottom, and you get -3/8. So this would be -3/8 points. All right. Now, since the third condition is not actually mathematically possible, you're really just going to combine these points here and these points here. All right. So what's the equivalent of 1/2 in terms of eighths? This would be equal to 4/8, right? The relationship 1 to 2 is the same as the relationship of 4 to 8. Right? So 4/8 positive minus 3 means that overall what you would get is a positive 1/8 points. Alright? So this is, and answers the question, based upon this information in the long run, would it be to an advantage or a disadvantage to guess at an answer? Right? In the long run, right, it would be an advantage. Right? It would be an advantage. How come? Because it's a positive expected value.
If you got a negative expected value, then you would say it would be a disadvantage in the long run to guess. Right? If you get 0 exactly, and that didn't happen in this case, then it would be neither an advantage nor disadvantage. It would be neutral. Okay? All right, 15, right? All right, this is about consecutive events, and we have two tools for this. We have the counting principle to figure out the total possible, I really should say the word permutations. All right, I think combos with a little asterisk, right, is a little bit more plain a way of talking. That's the only reason I would say that. All right. Calculate the total possible outcomes, i.e. the total sample points in the sample space, all right, for 2 consecutive probability experiments. Tossing a coin, which has 2 outcomes, heads or tails, let's just call it H and T, and rolling a 6-sided die, which again is 1, 2, 3, 4, 5, 6. All right, use either a tree diagram or the counting principle. Remember, the counting principle is the total number of outcomes of the first experiment times total of the second. All right, so how many outcomes are possible in this first experiment? I know it's weird to think of a coin toss as being an experiment, but in terms of math, it is. Right? There are 2, right? And on a 6-sided die, it is 6. So if we follow the counting principle, that's m times n, first times second, and if we had a third thing, we could do O, I guess. What's 2 times 6? It should be 12 total. All right? Permutations, really. I'm going to say combos, because again, I think that's just a more regular way of speaking and it's more relatable. Right? But when it didn't come up in this semester, just beware. There are something called combinations in math and permutations in math, and this resembles permutations, the results you're going to see. All right. Now, if you use a tree diagram instead, the benefit of doing that, aside from establishing this number, is that it shows you all of them. So it can be a little tedious, but let's say that you have a point of origin, and then you have the first experiment, and then you have the second experiment, and then together you have the sample space. All right. Here's the point of origin. The first one is the head, assuming this is the order, tossing a coin. You get a head or you can get a tail. 2 branches from the tree here. All right, now, following either one of these outcomes, all right, you have in the second experiment the die roll. So it would be 1, 2, 3, 4, 5, 6, and then you would have to write it again. 1, 2, 3, 4, 5, 6, and then draw branches to each of those. Like so. Okay. Now, if you connect them in sequence, head first and then 1, head first and then you roll a 2, head first and then you roll a 3, head first and roll a 4, and so forth, you'd see this is H1, H2, H3, H4, H5, and H6. All right? And then you do, assuming you start with tails, tails and then a 1, tails and then a 2, tails and then a 3. So you have T1 and T2, great movie, T3, T4, T5, T6. All right. How many points are there total? All right. These are sample points. Collectively, they are sample space. They're a set of essentially combos, which would really be more appropriate to call permutations. All right, because the order matters. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total, as predicted by the counting principle. Right. Okay. Now we're going to get into formulas. Buff, buff, buff. There you go. Okay. Let's see. The best thing I could tell you as you're doing this is to have those formulas either memorized or on hand as a reference. Right. A while ago, maybe a week or two ago, I forget now, I had made you a diagram that summarizes the formulas for this stuff. So I'm going to just point that really quickly. Essentially this page, right? And I think I scanned my own doodle here, but I was hoping that when you were watching that you would record it, because you're more inclined to remember something if you handwrite it. Anyhow, I'll remind you now. When you have OR type of problems, right, and you would know in this case because there's an OR here, right, that you're dealing with, one must consider whether the situation described is mutually exclusive or not mutually exclusive. Right? That decides which formula you're going to go with. Right? So, is this mutually exclusive or not mutually exclusive? Drawing a heart card or a face card, right? From a deck of 52, assume, right? In order to decide mutually exclusive or not mutually exclusive, you could phrase it to yourself this way: can a card be both a heart and a face at the same time? Right? And the answer to that question is yes, they can be. Right? Can be both. Right? So, not mutually exclusive. And in which case, if you had to, you would use this formula. The probability of event A or B would be equal to the probability of A by itself plus the probability of B by itself. And then you would have to subtract the situation where you have the probability of A and B. Right? Because you don't want to count something more than once. The situations of not mutually exclusive, you would end up having to subtract. There's an extra term in this addition. Alright? So, the answer to this is essentially not mutually exclusive. Alright? When you do the next one, alright, you're getting asked to decide mutually exclusive or not mutually exclusive. Alright? Drawing an ace, let's call it A. Alright? Or a queen. Alright? From a deck. Assume again 52. Alright? Ask yourself, can a card be both an ace and a queen at the same time? Alright? It's like, I'm trying to think of something that's not quantum mechanics. The playing cards is the best example. An ace and a queen cannot. Alright? These cannot coexist in the same card. Cannot be. Alright? So therefore they are mutually exclusive. Alright, and that would limit your formula that you elect from. The probability of an ace or Q, how to ask the calculator in this case, would be the probability of A by itself plus the probability of Q's, queens by itself. Okay? No third term, no subtraction, because mutually exclusive is just adding. Okay. Now when you get to 18, you go back to basically this question, which is why I took the time to write this formula. I'll scroll up here and just put that there. Erase this because it isn't necessary. And rephrase here. Slippery. All right. Calculate the probability, now do it, of drawing a heart or a face card from a standard deck of 52 playing cards. That means we're going to have to use the not mutually exclusive incarnation of the addition formulas, which means that it isn't just adding, it is subtracting out the instance where they occur in the same card. those conditions. All right. Let's figure out the probability of being a heart firstly. It's ironic I'm using black, right? I shouldn't use black. Because hearts are red. So we'll calculate the probability of a heart first. And in that case, how many hearts are there in a deck of 52? Right? It's an entire suit from ace through king, which is like 1 through 13. So this would be 13 out of 52. Okay. Losing my eyesight here. Okay. The other condition was face cards, so I'll just put, I'll keep this as blue and just draw a happy face here. In several places. Okay. How many face cards are there in a deck of 52? There are 3 face cards per suit. So there's 3 hearts, and then there's another 3 spades, and then another 3 diamonds, and then another 3 clubs. So 3 times 4 essentially. All right, which means that this fraction would be 12 out of 52 cards. All right. Now, how many are simultaneously both of these conditions? It's the AND situation. All right. This fraction, I'll use green reluctantly here. This fraction of things that are both a heart and a face card, there's a jack of hearts, a queen of hearts, and a king of hearts. This would be 3 out of 52. Let me see if that's visible. Somehow not. Sorry. Is that a little bit better? I swear that's a 52 there. The light is actually obscuring it weirdly. At least from my perspective. Plus, minus. Okay, so we follow the order of operations, which is that adding and subtracting are equally important, but you work from left to right. So if you add just the tops here, you get 25. If you take 25 and subtract out 3, what do you end up with? 22 out of 52. And ideally, you would simplify the fraction, right? They're both even, so you could divide both of them by 2. The answer to this 18 is 11 out of half of 52 is 26. All right, if you feel a little bit more comfortable writing it as a percentage, what would that be? Divide 11 by 26, and you get about 42%. 42%. That's exact. This is a rounded figure, but sometimes people like percents more. I do, personally. Not to corrupt you, all right? All right, now moving on. Dependent or independent events, beware. The English language gets you in trouble as a math teacher all the time, right? It's beautiful language and it has many eloquencies, if that's a phrase. But here's an example of that. I'm talking about the AND type of problem because that's what's here, all right? And over here on this side of the sentence is the word or, because you have to decide this or that, all right? Decide first whether the situation described are consecutive consecutive events that are dependent or consecutive events that are independent. Let me erase a little bit because there's too much gobbledygook in the way. This is distracting, so adios. So we're talking about consecutive events, and that will, again, we have to decide dependent or independent because that affects the formula that we will choose, that will decide the formula. All right, we have dependent, and this is the formula, and then there's another one. It's a little sloppy, as you can see, because I hand wrote it, but I will write it again. All right, drawing a queen from a deck. And then a second queen. The key phrase here is without replacing the first. So if you have consecutive events without replacement, as being described here, all right, that indicates, all right, that these are dependent, describing dependent events. The second is dependent upon the first. Second event dependent upon dependent first, right? Because it's without replacement. If they were independent, one event would have no bearing on the other. Right? That's why I put this here. Ask yourself, does one event have any bearing upon the other? Right? They do. That makes them dependent. We're talking about a dependent situation. All right. Calculate the probability of drawing two queens consecutively and without replacement. So the formula would be basically this. Green again. I want to write on top of it, so faintness of it is not such an issue. The probability of event A and event B, according to the dependent formulas, is this. The probability of A times the probability of B given A occurred. And that's kind of faint, so I will read it to you if it makes more sense. All right. The probability of A and B, the independent or dependent type of problems, all right, are consecutive events with or without replacement, is multiplication. So it's going to be the probability of A by itself, right, times the probability of B, but because of the conditions of A, it's going to be described as given A occurred, rather than independently. So, if you choose first queen, right, how many queens are there out of 52? Right. There are 4 from the get-go. So this is 4 out of 52. Right, that's the probability of drawing the first queen. The probability, you could label it like this, Q1 and Q2 if you like. Right. 4 out of 52. Right. When you talk about the second queen, how many would there be now if one was already plucked out of it and not shoved back in the deck? 3, right? So you're going to have 3 here. But at the same time, there's another condition you have to worry about. How many total cards would there be without replacement also as a condition? There would be fewer cards than be 51. Right? So those are your fractions. You have 4 over 52 times 3 over 51. Sometimes it's just this number that changes, the total just changes, because you're talking about a different thing like an ace, maybe. But since you're talking about 2 queens, and one of them is already regarded as having taken out, all right, you'd have fewer to choose from. Right? This ends up being kind of a crummy fraction, because you could do a little bit of simplifying up front, or brute force top times top and bottom times bottom. I would try to simplify first, regardless of whether you're using a calculator or not. This is even, they're both divisible by 4 actually. 4 divided by itself is 1, 52 divided by 4 is 13. These are also simplifiable, right? They're both divisible by 3. 3 divided by itself is 1. 51 divided by 3 is, let's see, goes into itself 1, so 2 up to 17. Okay? So these are not great numbers either, because they're sort of outside the realm of familiar, but they're definitely going to be better than 52 times 51, which is a much, even if you try to use your calculator to simplify, if you have a 4-digit denominator, it's not going to work. Not on that type. Right? So 1 times 1 left over is 1. 13 times 17 is 221. Right? If you wanted to get it as a percentage, just to see hypothetically, it's like, it's not even a whole percent. It's like 0.45%. Right? That's a decimal there, even after the fact of converting it to a percentage. So it's like really puny. Right? Just going to sleep. Don't go to sleep, please. I know I'm boring, but not that boring. Right? You're my computer. 1 divided by 221. Yeah. Okay. See, here's the decimal equivalent. And then if you convert it to a percentage, you're multiplying by 100, right? So the decimal moves to there. Right? So not even a whole percentage, right, of a chance. Right? 1 out of 221. Right, now the next one, this is conditional probability. It incorporates the word and as well. But it's a specific formula. Yeah, again, if I were trying to distinguish one from the other, you are looking for the phrase given that in the context of the problem. Right. But this is the formula that I would regard as the easiest formula. This is and, but it's more or less in the context of something, not exclusively, but of something, two conditions, both conditions, rather than consecutive events. You could probably apply this to consecutive events, but it might be overkill. All right, here's the formula. The probability of event 2 given event 1. This is the shorthand notation. This line, remember, is the phrase given that. There's lots of different books have different versions of this, but the most concise way of writing it, I feel, is like this. The number of outcomes favorable to the intersection of event 1 and event 2 over the number of outcomes favorable to event 1 specifically. Right? That's an intersection symbol, which is why I say something that is both conditions simultaneously. Right? I'm just trying to be cute by sticking an and in here because it looks like that to me. And this is the arrangement, right? This is event 2, which is usually, not exclusively, but usually the more specific condition. Right? It can be phrased differently, you know. And this is a little less specific, right? So, calculate the probability of getting an A at random. Given that, right, you get a grade higher than D. Right? So this phrase, for shorthand purposes, I'm going to write it as grade. I'm going to use the greater than symbol, and I'm going to use the letter D to describe this a little bit more concisely. Right. So to take this information and transport it into the model, all right, I'll put it here again in green because I can write on top of that pretty easily. I would do it this way. Yes, green is such a nice color that it doesn't work. Okay. Event 2 is the thing that is intuitively first in the sentence, weirdly, right? Perhaps that's counterintuitive. Getting an A, right? Given that, and then the thing that follows the phrase is follows in the sentence. Grade higher than D. Right, would therefore be equal to grade higher than D and simultaneously, because it's an intersection, an A out of the number of events that are outcomes that are favorable to the event of a grade greater than D. All right. Here's the set, just to make it a little bit larger, easier to see. A, B, C, D, F. All right. Now, I think when I did this as an example a while ago, I put I as well, because that's in theory possible. But and if you wanted to apply it to the Middlesex County College system, there would be some pluses in here, B plus and so forth, and minuses. So anyhow, this, for the sake of simplicity, all right, let's consider the intersection of these two conditions. Grades higher than D. All right, grades higher than D would be this group here. All right. What about this condition? Things that are an A entirely are a subset of that. All right, so it's just that. So how many of those are there total? that are an intersection of this condition and these conditions. This is three things, this is one thing, and they overlap in exactly one place. So this would be a 1 as the number of that intersection. All right, how many things again are grades total? Grades greater than D total, there's 3 things. All right, so this is 1/3, right? In the style of a percentage, 33 1/3%. Okay. Now, as an afterthought, I made an extra credit question. It doesn't matter actually, but let me just do this. I swiped this from your My Labs as well. There's a formula, so I would feel remiss without having talked about it today. I did a while ago, of course, but let me just describe this. This is something called expected value and fair price. All right, it's from that same section. Fair price to pay for something would be equal to the sum of the expected value, which you could calculate if you had to. That formula P1 A1 plus P2 A2. Plus the cost to play a game of some sort. Okay. What is fair price? The price you would actually have to pay, or what you would pay instead to break even. Which means you neither lost nor you won, right? A condition of basically 0, neither lost nor win. Right? In the expected value, right? The expected value for a lottery ticket is -$1. Why? Because you're spending $1. So -$1. Whereas the cost to play the game is $8. So you put plus $8. If you did the simple arithmetic, what would that be? All right, what's essentially 8 minus 1? Positive $7. That's the fair price, right? So rather than pay 8, an actual fair price, in which case you would break even, all right, would be $7 instead. Okay? That's that. Okay. Okay. That's it for today. Let me turn this off here. All right. As I said, remember your My Labs are due tonight. This evening. So spend the time, please, finishing that up. All right. You don't have to submit anything for this test. I'm just giving it to you again as a freebie. All right, and then I'll message you again on Thursday. All right, insofar as the final is concerned. Okay. All right. Thank you guys for sticking with me, and I'll see you on Thursday. Be careful out there.